And also, with the lecture, every week I'm going to be giving a problem set, which is obviously going to be optional. After the lecture. The problem set is just to give you guys some interesting questions to take a look at if you want. And you can submit it to mathcord.pset.submissions@gmail.com, and this email will also be on the problem set itself. So you don't need to write anything down. I think also if anyone here has knowledge of mathematical logic or model theory, an extensive knowledge, so enough that they feel comfortable doing so, if you could reach out and we can maybe see if you can help with this theory or anything sort of type, that would be great. Okay. I don't need to be here. Okay. Okay, let's begin. Let's start with talking about what mathematical logic is. It's a metamathematical sort of study of math itself. It studies sort of things that we can say about math, the things about mathematical objects, what sort of mathematical objects satisfy those statements, how we can sort of manipulate those statements and them still remain true in some mathematical objects, things like that. But I think really the best way to understand what mathematical logic is to actually do it. So let's start with the most simple logic, which is called a propositional logic. So a little warning, this lecture and the third lecture are going to be very definition heavy and not so interesting, in my opinion. By that I mean that the other lectures are much more interesting. But so just keep that. If you're bored by this lecture, next week should be much. Okay. By the way, yeah. Okay. Let's start with a definition. Oh, the prereqs to this lecture. The prereqs in general is, I assume that you guys know what the equivalent of a discrete math course. So like naive set theory. So you guys should know what a function is, and that's about it. And like cardinalities and stuff like that. Okay. Okay. Let's start with the definition. A Boolean function is a function from the set 0, 1 to the power of n to 0, 1. So what this set on the left is, it's a tuple of Boolean values, zeros and ones. It's out a Boolean value. Another way we can write this is 2 to the power of n to 2. So 2 represents the set 0, 1. And so when I'm lazy, instead of writing this whole set out, I'll just write 2. Okay. For n greater than 0. So for some positive n. Okay. Another definition is a connective is a symbol S with an associated Boolean function. So, sorry, with an associated Boolean function. So for example, I can define the connective and, so which we will denote, which will be given the symbol of for this wedge. It's also called a conjunction. And we can define it. It's a Boolean. It will be given a function from 0, 1 squared to 0, 1. So it's a Boolean, it's a binary Boolean function, which is a bit of a mouthful. But what that means is it takes two inputs and it gives me out an output. So we can go through all the possible inputs. So the possible inputs are 1 and 1, 1 and 0, 0 and 1, and 0 and 0. And the outputs, so 1 and 1 is going to be 1, because if I say something, so let's say I say it's raining outside, or the sky is blue and clouds are grayish white, that's a true statement. But if I were to say the sky is blue and clouds are purple, that's a false statement. So true and false is false. False and true is similar going to be false, and false is also going to be false. I can define a bunch more connectives, which we'll get to after I finish this definition, which is simply a set of connectives called logical signature. So I put logical in parentheses just because sometimes I'm going to be lazy and just call it a signature. Okay, so let's get on with some more connectives. So we have and, so we're also going to need or, which is also called a disjunction. And we're going to define it similarly with this table. So true or true is going to obviously be true. And an important thing to note here, not obviously. An important thing is a disjunction is not exclusive. So normally if I can say you can have the banana or you can have the apple, I mean that you can have one or the other. I mean, here a disjunction just means that one of them is true. It's true or Y is true, or both of them are true. So if I say true, or so let's say everything is either a banana or not a banana. Well, that's not a great example because everything is either everything is either a metal or not silver. Things can also not be silver and a metal, but what I said is a true statement. Yeah, exactly. It's an inclusive or not an exclusive or. I don't know why I'm getting caught up in that. But anyway, so another thing, if I say something true or something false, it's still true, true. And finally, if I say two false things that are disjunction is going to be false. Okay. And two more. Let's define negation, which has this little symbol as its representative symbol. And this is so these two are binary, right? These two connectives are binary. And this one is going to be unary. So it only takes one input as one value as input. So it just takes its input and just reverses it. So true becomes false and false becomes true. And our final connective is implication. Which gets a little arrow. arrow gets a little arrow as its input, as its symbol. It's also binary. 1 1 0 0 1 0 1 0. And okay, true implies true. That's going to be true. True implies false. That's going to be false, right? If I say if it's cloudy, then it's raining, then that is a false statement, right? Because it can sometimes be cloudy, but not be raining. So there's a point where true does not imply false, because here is when the first thing is true, then the second thing also has to be true. And from that logic, so what I'm saying is when the first thing is true and then the second thing has to be true, what if the first thing is false? Then what I've said is not necessarily false. So we just kind of sort of give the benefit of the doubt and make the last two things true. And we'll see later when you do proofs, it makes a lot more sense why we make these things true. Also take note that if we didn't make them true and we made them false, it would just be a conjunction. But okay. Okay. Say I want, so I have conjunction, so I can write X and Y, and X or Y, or X implies Y. But I want to be able to write things like X and Y implies Z, right? Or I guess X and Y implies X. Yeah. Though I don't want to keep on going back through my definitions because I do want to finish the lecture at some point. Okay, so firstly, a Boolean function is just, again, it's just a function from Boolean values. So it gets a couple of Boolean values and spits out a Boolean value. Connective is a symbol. Oh, yeah, if you're recording it and send it, but I'll just go through it now. A connective is a symbol that has an associated Boolean function. For example, we just defined 4 of them. So okay. Connective is a set of connectives. So here we have conjunction, which we see it's a binary Boolean function. It takes 2 inputs, and then we defined here what the output is. So right, these are the inputs, and this is the output. Okay, and so on. Okay. Okay. Now our next definition. This is going to be a nice little definition. This is how we start to separate ourselves from a discrete math course. Is suppose we have a set V of variable symbols. So these are symbols. And L, a logical signature. We define F sub L of V to be the set of propositional formulas over the signature L with variables from V. So that's a bit of a mouthful. Over the signature L with variables from V. Okay. This is not the definition. This is just the name of the definition. I'm also going to be writing this. I'm gonna not. Generally, I'm just going to neglect the V and write this as F sub L. And we're going to call these propositional formulas instead of propositional formulas over the signature L with variables from V, because that's just too long. So we're going to start by defining this. We define the set FLV recursively. So first, we need like a base case for our recursion. If P in V is a propositional variable, then P in V, then P is going to be a formula. These are called prime formulas. So we can call them propositional variables or prime formulas. By set, I mean, we're not, okay. I think an important thing for us for me to say at the beginning is mathematical logic cares, we're not going to be looking at mathematical logic formalization of math. We're going to be looking at it as sort of what can we learn about math. So when I say set, I mean set in any other sense that you would learn math. It's a collection of things. Here, yes, in a model of ZF, this does define a set. But you don't be concerned about the formalization of everything. That's just not the purpose. Okay, chill. If S in L is a connective, right? So it's a symbol, right? It's a symbol. It also has a. Oh, okay, that's fine. So if S and L is a connective, so that means it's a symbol, and it has an associated Boolean function, but we're going to ignore the Boolean function for now. So if S and L is a connective, and phi1 through phi n are formulas, then S phi1, phi n, this is a string. So basically I've taken S and I've concatenated it with the rest of the strings, is also a formula. Okay, so let's look at some examples. So let L be this sort of standard signature. So it has negation, conjunction, and disjunction. And we define V to be like P1, P2, P3, and so on. And so we have countably infinite many symbols, variable symbols. So for example, P1 is a form because of the first point. The negation of P1 is a formula because we look at S. For this S, we take the negation, and we take phi1. So it's here it's a connective of arity n. Right. So by arity, I mean that its associated Boolean function has an arity of n. So negation, right, is a unary function, so it has an arity of 1. Conjunction is a binary function, so it has an arity of 2. So and P1, P2 is a formula. I can also do and P1 or P2, P3. That's also a formula. Yeah, so these stuff like this, I can get a little crazy. And or negation, P2, and P1, P3. Stuff like that. I can just throw stuff around and I have formulas. But these are obviously not very readable formulas, right? Because what we're using here is something called prefix or Polish notation, where our connectives are at the beginning. But we're more used to something called infix notation, where our connectives are in the middle. So we're going to adopt the custom that if I have a binary connective, instead of circle v psi, I will write v circle psi in parentheses. So these get translated to P1, negation of P1. Now instead of and P1, P2, I'm going to write P1 and P2 in parentheses. The next one becomes P1 and P2 or P3. And this one becomes P1 or negation of P2 and P1 and P3. All that in parentheses. So this is just a syntactic thing, but it's more readable. Okay. Now, again, these formulas right now are strings, right? We haven't assigned to them any special property, any special value. They're just a set of strings with a special property. So keep that in mind for right now. And also keep in mind that I didn't really define a set of propositional formulas. I defined two properties that it should have. And I want it to be the smallest set which has these two properties. So how do we really know that such a set exists? Well, that's a great question. What we're going to do is we're going to look at all the sets. Here I'm going to do a little side note. We're going to look at all the sets S. Let B. We're going to define C to be all the sets S. S set of strings. S as properties 1 and 2. So we have a collection of sets of strings. And then I'm simply going to define f of L to be equal to the intersection of C. So this obviously is going to be the smallest. It's going to be smaller than all the sets in C. And it also is going to have these two properties. I'm going to leave the proof that it has these two properties to you guys as an exercise. But it's not that hard. And this is well defined in C itself is not a class, it is a proper set because the set of strings is a proper set, and I'm looking at all the subsets of all the subsets of the set of strings which has a certain property which is definable. So if whoever was asking about ZFC, this is well defined. This is not a class. This is well defined. It's not a class. Okay. Okay. So from what I just said before, we get the lemma. So literally, from it being the smallest set with these two properties, we get the following lemma called the lemma of formula induction. So the lemma says, let E be a property of strings. So what that means is that we can think of it formally as it's a subset of all the sets of strings. And so either something has the property, so it's in the set E, or it doesn't have the property, and it's not in the set E. And I'm going to write that if phi has the property E, we write E phi. More formally, we would write phi is in E. No, so okay, so you cannot have a string that looks like OR P. You would have to have OR PQ. The reason why, because if S and L has an arity of n, right? So OR has an arity of 2. So you need to have two formulas. My lecture notes will be available I'll post them somewhere, and they'll be readily available for all of you. Okay, so let E be a property of strings, such that one for every P in V, or I can also write, I'm going to adopt this notation from one, pi in FL prime. I'm saying that I have a prime formula, right? A prime formula is the same as a propositional variable. So for every prime formula, E pi. So every prime formula has this, every prime formula has this property. And 2, if phi1 through phi n in FL also have this property, then ES phi1 phi n. So so I'm looking at S in L with arity n. So now basically, so every prime formula has its property, and if phi1 through phi n are formulas with this property, then S of phi1 through phi n also has this property. So if E has these two, if the property E has these two characteristics, so 1 and 2, then E phi for every formula phi. So that's what the lemma tells us. So for example, let's give a really simple example. This is actually very important, called the unique reconstruction property. And what it tells us is every formula E in FL has the form phi is equal to S F phi 1 through phi n for unique S in L phi 1 phi n in F of L. So what this tells us, every formula, I really should write every compound, so non-prime formulas. So here, these were called prime formulas. These are called compound formulas. So either a formula is compound or it's prime. Prime, yes. Prime and atomic, you can use different authors use them interchangeably. Okay. So what this for unique S L1 S and L phi 1 through phi n in F of L. So what this means is that if S phi 1 phi n is equal to T psi 1 psi m, then n is equal to m, S is equal to T, and phi 1 is equal to psi 1, and up to phi n is equal to psi n. So basically what this means is if I have a formula phi, let's say, for example, which is equal to alpha and beta, it can't all of a sudden be equal to gamma and delta, or gamma or epsilon and epsilon beta, stuff like that. So if I have a formula as a single, you get to hear Sharp's voice when he starts talking about model theory, which is later on, like late lectures or early. It really depends when he wants to start. But just ask him to hear his voice if you're that obsessed with him. I'm sure he just think. Yeah. Okay. And the proof, trivial. The proof is trivial because of this point here. It's the smallest set which has all these properties. And if you look at E, it has these properties. Yeah, I know it's in the recording. That's why I did it. Okay. So, oh, no, sorry, my bad. The proof is not trivial. I was thinking a different thing. The proof of this proof is trivial. This proof is non-trivial. The unique reconstruction property is a very important property whose proof is non-trivial. I'm using OneNote. Rice, you use OneNote. Okay. Anyway. So the proof of the existence of such a form is by induction. So we define E to be the property if phi is a compound formula, then phi equals S phi 1 through phi n for S in L, phi 1 through phi n in FL. So this is our property. And I want to do formula induction on it. Okay. So one, if pi in FL is a prime formula, then E pi holds vacuously. I actually don't know how to spell that off the top of my head. So vacuously. Why does this hold vacuously? Because it's not a compound formula. Right, so what we said before is that if x implies y, but x is false, then that holds vacuously. That always holds. And if we look at this truth table, implication always holds. So these things are called vacuous truths. Because they hold because the premise doesn't hold. I see you edited that. Okay. 2. So let phi 1, phi n be formulas such that E phi 1, E phi n, and S and L. Then E S phi 1 through phi n, then E S phi 1 phi n obviously holds because we just take S to be S and phi 1 through phi n to be phi 1 through phi n. So E S phi 1 phi n. And so then by formula induction, E phi for all phi in FL. Yeah, so we get that E holds for every formula. So we get the existence of this form. Now, the uniqueness of this form is just a syntactic sort of argument that you can find in my lecture notes. I'm not going to prove it here. Okay, but the use of the unique formula reconstruction property, reconstruction, is that we can define functions recursively on formulas using it. So if I have a function, if we have a function f, we can define it. Well, here, maybe more clearly, we can define a function f f on f sub l by 1 defining f pi for pi prime, and 2 defining f s phi 1 phi n for s phi 1 phi n, s and l phi 1 phi n, and fl. So for example, let's say I wanted to define the subformulas of phi. So it's going to give me psi. Psi is a subformula of phi. Oh, I forgot to say, okay, my lecture notes, like I said, I'm going to post them after the lecture. I'm doing that just in case there are any issues in my lecture notes so I can fix them after the lecture. So I'll notice them during the lecture and then I'll fix them after. I will post that in this channel. And for, I'm sorry, I meant to say this at the beginning, but the textbook that we're following for mathematical logic is called A Concise Introduction to Mathematical Logic by Wolfgang Rottenberg. It's a great book. It's a little hard to read, but it's a great book. And I assume that everyone here, yeah, I mean, I don't assume that everyone here is going to read it, but it's a great book if you want to read it. Okay. Okay, so how do we define this? First, we define SF pi for prime pi, and that's just going to be pi itself, right? The subformulas of prime. I'm covering it now. Don't worry. So the subformulas of a prime formula is just the prime formula itself, because there are no smaller subformulas. It's atomic. And then the subformulas for S phi 1 phi n is going to be S phi 1 phi n. So it's the whole formula. And the union from I equals 1 to n are the subformulas of phi I. So we need to, so this is the definition of the set of subformulas. Okay. So we show two things, right? One, basically we need to show that it's well defined. And to show that it's well defined, we need to show that this covers for every phi in FL, SF phi is defined. Now, why is this true? Why is this true? It's because of the unique reconstruction property, because of the existence of the existence part of the unique reconstruction property. Every formula has this form. It has the form S phi 1 through phi n, or its prime. So every formula has this sort. So it either has the form from 1 or the form from 2, and it's well defined. And so SF phi has a unique value, right? So I can't map one value to two different values. And this is because of the uniqueness part of the reconstruction for lemma. And that's because I can't have that, right? S phi 1 phi n can't all of a sudden, right? I can't have that, sorry. That S phi 1 through phi n is all of a sudden equal to T psi 1 psi m, right? And then they would have different subformula. So they can't have, everything has a unique form, which looks like this, and then you just define it on that form. No, yes. So E can be seen. So E can be seen as a function from formulas 0, 1, but this is just equivalent. Well, that's not. It's equivalent to seeing it as a subset of F of all the formulas, right? And this is sort of how you show, right? There is a bijection, right? A very, very canonical isomorphism between functions from 2x and power sets of x. Yeah. No. So what the unique reconstruction property says, so what it says is that if you have a formula, there is a single way of getting from the connectives and the prime formulas to that formula, right? I can't start with, I can't go from, right? If I have P or Q, or here, maybe formulate, or P and Q, I know what all the stuff, I know how I got started with, and I started with Q, R, I added an and before them, then I took a P and I added an or before it, right? I know exactly how I got there. There's no two ways to get there. They're not sets, they're formulas. Each, okay. Um, Another example is it's to find the variables in a formula. So var phi is going to be equal to P in V. P is a variable in phi. So 1 var pi is just going to equal pi for prime pi. And 2 var s phi 1 phi n is going to be the union of the variables in its subformula. So we're doing chapter, that's a good question. I think it's 1, so it's 1.1 and 1.2. Okay. This can also note that we don't really need this to define the variables in phi. Yes, var phi or the prime subform. Yes, so you can view it. So you don't need this for this this recursive definition. You can literally define it as P and V, right? Like there exists an I such that phi at the place I is equal to P. Or you can define it using subformulas. You can do the subformulas of V with the intersection of V, intersect V. But yeah. Okay. So, okay. Now we're going to use this idea of the formula of defining functions and formulas using recursion to define our main sort of object for today. Let W1 to V, from V to 0, 1 be a valuation. So a valuation is just a function which for every variable assigns it a truth value. So it's either 0 or 1. We extend it to a function. We're going to give it the same name. It's also going to be called W, but now it's going to take a formula and give it a truth value. So for example, let's say I have W and I have P1, P2, P3, and it assigns to P1, 1, P2, 0, and P3, 1. And now I have the formula P1 and P2 or P3, right? W should then assign to this the value of 1. Yeah, so that's sort of the idea of extending W from assigning values to variables to now assigning values to formulas. And we're going to do this through formula recursion. So 1 for a prime, W pi is already defined. Why is it already defined? Because pi is literally in V, and we start with the function from V to 0, 1. For S in L, phi 1, phi n in FL, W of S phi 1 phi n is going to equal S, right? S is a connective, so it's a symbol, but it has an associated Boolean function. So it's always a function. So S of W phi 1, W phi n. So for example, W of phi and psi is equal to W of phi and, or I'll write it like this, the conjunction of W phi, W psi. Yeah. So if W phi is given the value of 1 and W psi is given the value of 0, then W phi and psi is given the value of 0. Okay, and we write, here's just a little thing I'm writing it here for the problem set. I'm not going to use this notation in the lecture. Next lecture we will, but we write satisfies phi if W phi is equal to 1. That's our definition. This symbol is called the satisfaction relation. Oh, what? Sorry. Relation. And this is a very important relation that we will talk about, that we're basically going to be looking at today and next lecture. And let's talk about our first lemma, which we'll call the consequence lemma, which is not to be confused. We'll also talk about a consequence relation next time, and that's not to be confused. That has nothing to do with this lemma. But okay, let W and W tag, W be valuations which agree on var phi, which means that WP equals W tag P for all P in var phi. Then W phi equals W phi, W phi equals W prime phi. So so basically what this means is that the valuation of a formula depends only on the valuation of the variables in that formula. So the proof is easy formula induction. Okay, and what this means is, suppose var phi is, so this is some new notation that I'm going to be introducing. Let's say var phi is contained in P1 through Pn. Then I'm going to write phi equals phi P1 through Pn. So this notation means that I'm listing the variables that exist in phi. And if x1 through n are Boolean values, we write phi x1 xn to equal w phi, where wpi is equal to xi. Okay, this is a bit of a lot of words and not a lot of explanation, but what it pretty much means is that if I have a formula whose variables are p1 through pn, and then I take Boolean values x1 through xn, write phi of n through xn to be the of phi when I substitute xi for pi. So for example, if phi is equal to p and q or r, then I'll write phi equals phi p q r, and phi 1 0 1 is going to equal to 1. And this is well defined. This here is well defined because it doesn't matter what w is defined on for the other propositional variables, right? By the consequence lemma, we only care about, for the valuation of phi, we only care about w's value on the variables in phi. No, it's not an axiom. it is, like I said, it's provable. It's just it's an easy proof. Yeah. Okay. What next? Okay. Okay. Suppose for every natural number n, Pn. So in this, yeah, so Pn is in V. I have some symbol called P sub n. Define FLN to equal V in FL. This is just some quick notation, such that var phi is contained in P1 through Pn. So F sub L n. Oh, why is evaluation equal to 1? Because if you look at this, right, if you look at this, I get 1 and 0 or 1, which is going to be equal to 0 or 1, which is equal to 1. Okay, so F sub L of n is just all the variables whose all the formulas whose variables are contained in P1 through Pn. Definition: let F be a Boolean function it is represented by phi in F sub L of n if and only if f x1 xn is equal to phi x1 xn for all x1 xn in 0, 1. So a Boolean function is represented by a formula if for all inputs they agree. So for example, if I look at the function of the implication function, so right, implication is represented by the negation of P1 and negation of P2, or negation of P1 or P2. Right, these are two representations of implication over the signature negation, conjunction, disjunction. Okay. Okay. And equivalence. So I'll quickly define another. I'll quickly define another connective called equivalence, which is a double arrow, and its definition is just going to be if the two inputs are equal to each other. Can be represented by P1 implies P2 and P2 implies P1. Okay. Oh, okay, nice. Phi and psi in FL are logically equivalent, denoted phi is equivalent to psi, if and only if W phi equals W psi for all valuations W. Um, we will talk about the Kaiser. Is it Kaiser? But I don't know how to pronounce his name actually. Kaiser Shelach theorem later on, and Sheli Shelach is just a pun in Hebrew. Okay, so two things are logically equivalent if for any valuation, their values on that valuation are equal. So for example, if alpha, beta, and gamma are formulas, then alpha and beta and gamma is going to be equivalent to alpha and beta and gamma. And similarly, alpha or beta or gamma is equivalent to alpha or beta or gamma. Right, so we have these are associative. So conjunction and disjunction are associative. And similarly, they're also commutative. Alpha and beta is equivalent to beta and alpha. And alpha or beta is equivalent to beta or alpha. And some more stuff. De Morgan's law, these are important ones. The negation of alpha and beta is equivalent to the negation of alpha or the negation of beta. And the negation of alpha or beta is equivalent to the negation of alpha and the negation of beta. What this means, okay, take this last point. These are called De Morgan's laws. And what they tell us is that conjunction is representable in the signature with only disjunction, and disjunction is representable in the signature with negation and only conjunction. So in order to represent conjunctions, we only need negation and disjunction, and to represent disjunction, we only need negation and conjunction. Okay. Now, oh, and a last, and we're going to define two symbols here. T is going to equal P1 or not P1, and bot or false is going to equal P1 and not P1. So notice that WT is equal to 1 and W bot is W bot, whatever, is equal to 0 for all W. So T represents truth and bot represents false. Sometimes we're also going to want that T and bot in or perp are in our logical signature, but it doesn't really matter. Okay. So these, we can think of T and bot as like sort of Boolean constants. Okay. Yeah, and another one, a very interesting, okay, we're going to take the convention that alpha implies beta implies gamma equals alpha implies beta implies gamma. So implication is right associative. And if we do that, then we have the following nice identity. Alpha 1 implies alpha 2 implies alpha 3, and so on, alpha n implies beta is equivalent to the conjunction of all the alpha i's implying beta, where alpha I from I equals 1 to n is equal to alpha 1 conjunction with alpha n. No, we don't have for all. What I'm writing here is, this is just, I'm using for all as a in speech, right? I'm not writing it. So propositional logic, if we look at propositional logic, it's defined using only propositional variables and connective valuations. And so what I'm saying here is that T for every valuation, WT is equal to 1. That's not something in propositional logic. That's something I'm saying about propositional logic. Yeah, exactly. It's an external thing. So something to note is that equivalence is an equivalence relation. Remember, an equivalence relation is something that's reflexive, symmetric, and transitive. But this should not be surprising because its name is equivalence. But more so, it is a congruence, which means, what that means is that if S is an L and phi 1 is equivalent to psi 1 through phi n is equivalent to psi n, then S of phi 1 through phi n is to S of psi 1 through psi n. Right, so let's say, for example, I write if alpha is equivalent to beta and gamma is equivalent to delta, then alpha and beta is equivalent to gamma and delta. That's what this tells us. Okay, and we have this lemma called the replacement lemma. Says suppose alpha is equivalent to alpha prime, and phi is a formula. Let phi prime be obtained from phi by substituting one or more instances of alpha with alpha prime. Then phi is equivalent to phi prime. So basically, if I take a subformula phi and I replace it with an equivalent subformula, then the big phi, the formula phi, remains equivalent to the new formula phi prime. So let's say I write, so if alpha implies beta or gamma, right? I can replace alpha implies beta. We know that alpha implies beta is equivalent to not in negation of alpha or beta. So alpha implies beta, this is just equivalent to the negation of alpha or beta or gamma. These talks happen once a week on Mondays, 7 o'clock Universal Time. Okay, now let's get to the actual, we're going to finally actually prove something. Something nice. So first we need a definition. A literal is a prime formula or its negation. So very simple definition, right? It's either, so it's pi or negation of pi, and that's a literal. Let alpha I be a conjunction of literals. So right, it's of like, for example, P1 and not P2 and P3 and not P3, for example. That would be like an alpha I for I equals 1 through n. Then their disjunction is a disjunctive normal form, or for short, a DN. So for example, P1 and not P2, or P3 and P2 is a DNF. And similarly, we'll take the dual of this. Let beta I be a disjunction of literals for I equals 1 n. Then their conjunction is a conjunctive normal form, a CNF. So these two things, DNFs and CNFs, are very important. And why are they important? It's because of the following theorem. Every Boolean function can be represented by a DNF and a CNF. So if I have a Boolean function, I can represent it using a DNF and a CNF. And I can actually, yeah. And let's prove this. Let f from 0, 1, from 2 to the power of n to 2 be a Boolean function. And we're going to define phi to be equal to the disjunction on all the vectors x, such that f of x is equal to 1, and then the conjunction of I equals 1, to n of pi to the power of xi. What does pi to the power of xi mean? Where p to the power of 1 is equal to p, and p to the power of 0 is equal to the negation of p. Okay, so for example, implication. Let's take a look at implication. Let's write down quickly the truth table for implication again. And that's 1, 0, 1, 1. So what we're going to, we have to take the disjunction over these three lines, these three vectors. So we have 3. So we're going to need 3 disjunctions. Well, I don't need that much room, but okay. And so P1 to the power of 1, so that's just P1 and P2. Or P1 to the power, so negation of P1 and P2. Or the negation of P1 and the negation of P2. So that's our disjunctive normal form for implication. Yeah. I think from this example, it's actually pretty clear why this is true. But one more thing to note is that this is not just a normal disjunctive normal form. This is a disjunctive normal form where all the conjunctions, all these inner things, have the same number of literals. So we can call this a standard form. So these are DNFs and CNFs in standard form, where the standard form means that all the conjunctions of the DNF or all the disjunctions of the CNF have the same number of, all use P1 through Pn, use the entirety of P1 through Pn. So for example, P1 or P1 and negation of P2 is not in standard form because the first conjunction does not use P2. Okay. Now all we need to do now is we need to prove that phi represents f of represents f. So pretty much what we need to do is we need to prove that W phi is equal to f of WP for all W. This is another way of saying that f of x is equal to f of x, right? Because I can just define WP is equal to x, and then f of x is equal to W phi, and f of WP is equal to f of x. Okay, so we just need, okay, for all W. Now, W phi is equal to 1 if and only if there exists an x with f of x equal 1 and WPI xi equals 1 for all I equals 1 through n. Yes, no, it's not of this 3ds, but that is that every Boolean function can be represented by a CNF with, is it 3 disjunctions? Yeah, I think it's 3 disjunctions, or every conjunction. I mean, I can't remember. I did a course in this, but I forgot already. But yeah, so there's yes, but we're not going to be talking about complexity theory in this course, because in this series, because that's just not our goal here is model theory. It's not complexity theory or proof theory. Okay, anyway, so W phi is equal to 1 if and only if there exists a vector x such that f of x is equal to 1 and WPI to the power of xi is equal to 1 for all I. Now, what does it mean for WP to the power of x to equal 1? I'm going to say that this is if and only if WP is equal to x. Now, notice that WP, if x is equal to 1, if x is equal to 1, then WPX is equal to 1 if and only if WP is equal to 1, which is equal to x, because p to the power of x is equal to p. And if x is equal to 0, then WP to the power of x is equal to 1 if and only if W negation of p is equal to 1, which is if and only if WP is equal to 0, which is equal to x. Okay, so we have here, so now if I continue, it's if and only if there's an x with f of x equals 1, and WPI is equal to xi, which is just another way of saying f of WP is equal to 1, right? Because what this thing is saying is that there exists a vector, there exists a vector x such that WP is equal to x. And so if WP is x, and I know that f of x is equal to 1, then f of WP is equal to 1. Okay, so that's our proof of everything having a DNF. Everything having a CNF, we can do similarly. Phi is equal to the conjunction of f of x equaling 0, and the conjunction for I equals 1 through n of pi negation of xi. That you can prove by yourselves. There's actually in the problem set, we're going to have we're going to prove this an alternative way. But okay. Now an obvious sort of thing that I glossed over is that two formulas represent the same Boolean function if and only if they are logically equivalent. If and only if they're equivalent. So what this tells us is every formula phi is equivalent to a DNF and CNF. The proof of this is that phi represents a function which is represented by a DNF and CNF. And what I said before is that if two things represent the same, if two things represent the same function, if two formulas represent the same function, then they're equivalent. So phi is equivalent to these DNF and CNF. Okay, so now my final definition is a logical signature is functional complete if every Boolean function can be represented by a formula over that logical signature. No, like actually don't think too hard about it. It's not important. Like I said before, we're not trying to formalize everything. Yeah, Sharp is right. Sharpie is always right. Take his word for it. Okay, so for example, we just showed that negation, conjunction, and disjunction is functional complete. It's functional complete. Why is it functional complete? Because a DNF and a CNF all they need are conjunctions and disjunctions. Is functional complete, but we just showed before that a conjunction can be represented by using disjunction and negation, and a disjunction can be represented using negation and conjunction. So this means that negation and conjunction is functional complete, and so is negation and disjunction functional complete. Like I said, this is because that using this signature, I can get disjunction, and using this signature, I can get conjunction. So using both of these signatures, I can get all three of these connectives, and that's what I need to have functional completeness. So now, so pretty much now what you want, if I want to show, let's say I want to show that a logical signature is functional complete, all I need to show is that I can represent negation with it, and I can represent conjunction with it. Or I can represent negation with it, and I can represent disjunction with it. Okay. And yeah, that's it for now. That's the first lecture. Like I said, we didn't really get into so much interesting stuff. I will be posting the lecture notes for, these are pre-edit lecture notes for the second lecture, along with the lecture notes for the first lecture. So you guys can look at those if you want. And I will also be sending the problem set. Again, you send it to us via email. If you don't feel comfortable sending stuff via email, you can DM me, and then we will go over your solutions, and we can give you we can review it, and we can give you feedback. And if you want, you can specify in your email or your DM if you want a numerical grade, and we can maybe give you a numerical grade just if that's something that you're into. And there is no submission deadline. You can submit whenever, and we will check it whenever. Okay. That's oh, Oh, sorry, Sharp. I didn't see that you requested to speak, but I'm going to reject it. I'm kidding. Yeah, I'm not going to enable your obsession. Yeah, exactly. What Ryan said. You have to, when studying logic, there's sort of meta language, and meta arguments. So these are arguments about the stuff that we're studying. And then there's stuff that you can talk about from within the logic. And you have to sort of keep in mind that these are two different things. No, no letter grades. I don't like letter grades. Oh, did he? Fine.
Uh, all right. So since people are, getting hung up on the like, oh, we're doing first order logic to talk about propositional. Okay, there's a few layers to exactly what's going on here, and there's like 5 different ways you can fix this problem. But the way we're doing it here, where we're considering genuine functions. So the point of this is to get to model theory, right? So we're considering set models of propositional logic in a sense, right? We're thinking sets, functions, and they behave under the rules of propositional logic. We're not formalizing propositional logic, we're studying it.
Yeah, that was a great, much better explanation. Um, yeah, that was good. Okay, so any other questions before we finish? Wait, Rice, did you already change your name? Oh, wait, so the idea for functional completeness, a function, there are two reasons why I want to talk about it. The first reason you could ask about it on that, and the second is because I wanted to. So then, when we're talking about first order logic, I don't want to do it over a general signature or a general logical signature. I want to talk about. I just want to use conjunction and negation. And the whole idea is that because it's functional complete, I don't need to be any more general than that. And also, even next lecture, we're not about over it over the signature of conjunction and negation. So that, and we're not using any generality because every Boolean function can be represented using the signature. It's not an exhaustive list. It's not like an exhaustive list. But there is a list of things that I put on the event panel, and that has pretty much the overview of what we're doing. The next lecture, we will talk about propositional compactness. So there's first order compactness, and propositional compactness. First order compactness is for first order logic, and propositional compactness is for propositional compactness. All we go through be true for propositional logic. Actually,
Some non-classical logics do have like versions of completeness, versions of compactness. compactness, completeness, and all that may or may not be genuinely the same thing for different logics. That's a whole can of worms. We're not touching that.
Yeah, because non-logical logics are for weird people. And my advisor does it, and he's not weird.
Whenever I get to like molecular things, I might end up mentioning like some non-classical ones, but that's more in the direction of like infinitary and additional quantifiers. We ain't touching like
and
intuitionism.
Mathcord sharp is weird, so my point stands. No offense. So the problem set will be sent on the events channel for now, as well as the lecture notes, and after I think a week, I will send the solution to the problem set, and that will be also in events. Yes. Yes, that's exactly why unique reconstruction matters for defining function via recursion. So we don't. So this server. Remember, this is a community server with hundreds of thousands of members. So we can't just create new channels willy-nilly. Bye, Valley. I'll talk with the other moderators about creating a thread. I was also considering that. But the issue is with creating a thread is that not everyone will be able to know in order to find it. And just it'll be harder for them to find it. Or people that just want to look at it won't be able to find it. Yes, I'm not gonna say that. To Layla's nemesis, you can reduce everything to beyond the problem set. Welcome for the lecture, and thank you to everyone for joining. It was a lot of fun, and if there are no more questions, I will see you all next week. And my emails, I guess. Oh, hey, Jix. Thanks, Hire. And yeah, okay. They're going to be as long as I feel like I can, as long as I need them to be in order to cover the material that I want to cover. I think we are going to, in order to fully understand how long these lectures are going to be. But if I had to guess, somewhere between an hour and a half to 2 hours. And if we get longer than that, then we might have to split it over 2 days.
Whenever my turn comes around, whenever Slurp, gets done whenever Slurp's done talking about propositional stuff, I'll be doing them shorter than that because, quite frankly, I don't have 2 hours in this time slot normally for this.
I guess maybe this makes sense to say in front of everyone, but Sharp, you can feel free to change the time when it gets to your gets to your turn. As long as everyone, like, as long as people are okay with that, I guess, because that it's on your hands. Okay, bye everyone.